to discuss one very important area of research, that is energy harvesting based reconfigure intelligent surface. So actually, the energy harvesting based reconfigure intelligent surface will be very promising because uh, because I think this will be very promising. But the thing is that there is no such hardware still available in the literature. Maybe some paper are there, theoretical paper, but hardware, I think I need to search if there's any hardware or not. Maybe I was searching, maybe there's no hardware available in this area, reconfiguration surface based energy harvesting. But theoretical people, they are publishing a lot of paper on energy harvesting, and they are saying that this RIS based energy harvesting will be very promising. Another thing is that today I'm going to discuss one very important area, that is the 6G communication. And for 6G communication, energy harvesting is one of the fundamental aspect of the 6G. So for 5G, we still don't have the energy harvesting, but for 6G, it will be integral part of energy harvesting. So as Dr. Anirban Kormkar told me to show some pictures of South Korea and our university. So that's why I included some picture. And this is in front of our university, this left picture. And these are the buildings. So beside this building, I have my own I have my own apartment here. And the right side is our university. And this is during winter time. There are a lot of buildings number in Korea. We have like building 8, building 9, like this type of thing. And this is another picture in South Korea. This is Jeju Island. This is very famous tourist destination in South Korea. And about temperature during winter, so the temperature is like maximum -4 degree, and maybe minimum will be maybe -16. Sometimes some area of Korea, the temperature is almost -30, something like that one. Maybe -34 something. So in this week here, I mean, there's no, I mean, only one day the, I mean, positive and all are negative. This type of temperature here. And oh, this one is our town. Our town is, I mean, 80 kilometer from Seoul, and this name of the town is Chonan. So I live here. I mean, I normally go to this shopping restaurant. This shopping center to buy vegetable. This is vegetable market, and this is our department. So this is our department. So there's a lot of building are there. Anyway, so today I'm going to discuss a very important area of the things that first I will going to discuss some introduction of the 6G communication and energy harvesting for 6G communication. Then I'm going to discuss literature review. And our designs, we have designed 1 bit transmitter array with beam steering capability. So this transmitter array, one type of IRS. And uh, for modern communication, we need both beam steering as well as fluorescent conversion, because with beam steering we can get the steer beam, and with fluorescent we can enhance the channel. I mean, we can enhance the channel capacity double. So we need both beam steering and fluorescent conversion. So today I'm going to discuss that our design of transmitter array with fluorescent conversion, and this transmitter array with both beam steering and fluorescent conversion capability. Next, I am going to discuss 2-bit reads with sensing capability and passive reads. And next, I will be discussing the conclusion section of our presentation. So the ongoing deployment of 5G cellular system is continuously exposing the inherent limitation of this system compared to its original promises as enabler of Internet of Things. These 5G drawbacks are spurring worldwide activity focused on defining the next generation 6G system that can truly integrate far-reaching applications ranging from autonomous system to extended reality. Despite recent 6G initiative, the fundamental architecture and performance component of 6G remain largely undefined. So in this lecture, I am going to discuss a forward-looking, holistic vision that define the tenet of 6G. In our opinion, that 6G will not be a mere exploration of more spectrum at higher frequency band, but it will be rather be a convergence of upcoming technology trending driven by exciting underlying services. So there are a lot of services are there, that is driving application and driving trend, enable technology. So first application in this case is the multi-sensory XR application. So XR will yield many killer application for 6G across the AR, MR and VR. So AR means augmented reality, MR means MR mixed reality, and VR is virtual reality. Upcoming 5G systems still fall short of providing a full immersive XR experience, capturing all sensory input due to its inability to deliver very low latency for the data rate intensive XR application. A truly immersive AR, MR, XR experience require a joint design integrated not only engineering but also perceptual requirements stemming from human sensory cognizant and philosophy and human sensory and other things. Minimal and maximum perceptual requirement are limited by the factor into the engineering process. So to do so, a new concept, that is the quality of physical experience, that is QoPA measure, is needed to merge physical factor from the human user itself for a classical QoS, that is quality of service, and QoE, that is uh, quality of service, and quality of QoE means quality of experience. And such factors that affect QoP include brain cognition, body um, physiology, and gesture. And driving this one is the fast driving application. Next, we have another driving application for 6G is the connecting robotics and autonomous system. So the primary driver behind 6G system is imminent deployment of this connected robotics and autonomous system, including drone delivery system, autonomous car, autonomous drone, swarm, vehicle, etc. So this one is the next driving application. Next, we have another application, that is brain computer interface. So this brain computer interface another is one of the important area for 6G. Also in 6G we have energy harvesting. So I will also discuss the energy harvesting, this area, that is the energy transfer and harvesting. So wireless brain computer interface. So beyond XR, tailoring wireless system to their human user is mandatory to support service with direct brain computer interface. Traditionally, brain computer interface applications were limited to healthcare scenario in which human can control prosthetic limbs or neighboring computing devices using brain implant. However, the recent advance of wireless brain computer interface and implant will revolutionize this field and introduce new user scenario that require 6G connectivity. Such scenario range from enabling brain control movie input to fully fledged multi-brain control cinema. So this one is the one third application. Another application is the blockchain and distributed ledger technology. So blockchain, and this is known as DLT, will be one of the most disruptive IoT technology. Blockchain and DLT application can be viewed as the next generation of distributed sensing service. Now we have next driving trend. So for 5G communication, we have some data. I mean, the data rate is very good one, but for 6G communication, we need 1,000 times more. I mean, 1,000 times more data compared to 5G communication, and data bits will be almost 1 terabyte per second. Now, for 1G to 5G communication, all the communications were, I mean, only a two-dimensional communication system. I mean, there is no drone or no flying vehicles, but for 6G communication, and the it will be the volumetric, spectral, and energy efficiency. And in this lecture, I'm going to discuss the smart surface and how we can fabricate smart surface and smart things. So this is another driving trend for 6G. Massive availability of small data in 5G communication, and nowadays most of the data are in data center. But in 6G communication, it is predicted that the data will not be in data center, but it will be also, there will be a lot of small number of data centers, small data center, and data will be distributed across all network. And from SON to self-sustaining network. So SON has not been only scarcely integrated into 4G or 5G works due to lack of real-world application. However, different application like connecting robotics or maybe DLT application, this this SON and self-sustaining network will be very important. And this SO6G will require a paradigm shift from classical SON, whereby the network merely adapted function to specific network state, into a self-sustaining network that can maintain its key performance indicator under highly dynamic and complex environment stemming from rich 6G application domains. And next thing is that convergence of communication, sensing, and convergence of communication, sensing, control, localization, and computing. When we are talking about the 5G, 1G communication to 5G communication, most of the communication are only the tracks of this communication is only the wireless communication. But for 6G communication, it is expected that it will be not only working as a wireless communication, but it will have also sensing capability. Also, it will have control and localization computing, etc. And it is expected that for 6G communication, the smartphone will no longer be important things, because some watch or wearable devices or plain implantable things. So the the smartphone will not be so useful in 6G communication, because there will be a lot of other technology like wearable technology, enable technologies. So in 5G communication, until 5G communication, maybe in 5G communication, people are using still millimeter wave like 28 gigahertz, but in 6G communication, all frequency will be used. That is below 6 gigahertz frequency, millimeter wave frequency, also terahertz frequency. Also, some people are saying that it will be integrated also optical communication in 6G communication. But a lot of people are saying, but but I don't know whether optical communication will be there or not. Enable technology. So in normal communication, I mean, on 1G to 5G communication, we have only one frequency. I mean, the transmitter are only one, design only one frequency. But for 6G communication, the transmitter will have need to radiate multiple frequency, not only sub 6 GHz frequency, but also terahertz frequency or millimeter wave. So we need to design the transmitter in such a way that it can transmit a multiple frequency. Also in 6G communication, we are going to use the terahertz frequency, but the problem with terahertz frequency or higher frequency is that these loss are very high. Another important thing for this frequency is that um, it is traveling like light. So yeah, I mean, like it's travel like light. So we need to have some mechanism through which we can reflect the signal, and the signal can reach to destination. And another NL technology is the edge AI. So edge AI will be another important area of research for 6G communication, and edge AI will be integrated with 6G and 5G communication. We still don't have the total AI integration, but 6G communication we can integrate. Also, a lot of people are saying the generative type of AI will be used, so they can generate the environment for surrounding things. After that, they can predict that what should be the next step, and according to that scenario, the signal will be transmitted to different locations. So this type of AI will be very important. So for 5G communication, we still don't have the satellite network integration or any drone integration into our network. But for 5G communication, 6G communication, it will all will be integrated with 6G communication. That is satellite network, terrestrial, airborne network, etc. Another topic is the energy harvesting. So in this short term, I mean this faculty development program is on energy harvesting. So energy harvesting will be integrated with the 6G communication, because the energy harvesting devices are still not ready. But it is expected that within 10 or 20 years, the energy harvesting devices will be very good one. So we can integrate the energy harvesting devices to 6G network, and something like if we want to suppose we have some sensor, we can send power for energy harvesting from this 6G tower, and from here we can sense the signal, and the signal can, I mean, the receiver will have some energy harvesting capability, and it can power itself, so we don't need any type of battery. Beyond 6G communication, what should be the, I mean, what is the beyond 6G, what is the beyond 6G? So beyond 6G, a lot of people are saying that quantum communication. So quantum computer is going, I mean, nowadays, I mean, a lot of companies are proposing different type of quantum processor. So maybe 10 or 20, after 10 or 20 years, the quantum computer will be, I mean, we can use quantum computers. So quantum computer will be integrated into this communication system, and this type of communication are known as quantum computing communication. This is beyond 6G communication. And another thing is that integration of RF and non-RF. So from 1G to 5G, we still don't have the integration of the RF and non-RF. But beyond 6G, there will be integration. I mean, there will be integration of 5G. I mean, RF and non-RF devices. So this is some overview of the 6G, and energy harvesting will be another important area for 6G application. Now in this talk, I'm going to discuss different type of deconfigured intelligent surface. Why we need deconfigured intelligent surface? So these surfaces are known as intelligent reflecting surface or a reconfigurable intelligent surface RIS. So if the frequency is very high, then the wave cannot travel from this base station to the mobile tower, the mobile user. But for below 6 GHz frequency, there will be some reflection or refraction, and it can reach very easily to the mobile user. But when the frequency is very high, then we need direct line of sight. For such scenario, uh, we need this type of a reconfigured intelligent surface, and this is the architecture of the reconfigured intelligent surface. We can use different type of PN diode or varactor diode or vanadium dioxide or different type of tuning devices to tune this type of RIS. So this is for normal wave. If the wave is coming from on, coming and impinging on a reflector, and the reflector, the going and the reflector, this is the reflector. So it follow the sense formula, but this anomalous reflection, this type of reflection, because this is the phase, one phase, another phase, another phase, so there will be some constructive interference at one particular point. So it is like anomalous reflection, and it does not follow the sense formula. So this is one my paper. So I'm going to discuss some of the hardware from this paper. So I can open. So RIS can be reflective type as well as transmittive type. So this IRS is the reflective type. So this is the one transmitter antenna, and this is the receiving antenna. So if we have IRS here, the signal can go this direction or this direction or this direction. So we can get a beam steering capability from this IRS. So this type of IRS is known as a reflective type, a reconfigured intelligent surface. So we have another type of IRS, and this IRS is known as the transmittive type reconfigured surface. For this type of IRS, we have one horn antenna here, and we have one transmitter here, we have another receiver here, and the receiver here. So when from here the signal can go this direction or any direction, so it will have some beam steering capability, and this type of IRS are also known as the transmitter array antenna. Now in this paper I have discussed a lot of theory review paper of IRS. So a lot of authors, they provided a review on this IRS. And for the normal conductor, if this is the conductor, so for this normal conductor we have eta s. So eta s is equal for all is equal, but for this reconfiguration surface the eta is different. So eta s1, eta s2, eta s3. So from each portion of this surface we will get one phase. From this surface we will get another phase. From this surface we will get another phase. So there will be phase variation across the surface. So from as there's a phase variation, so from this surface we will get one radiation and another radiation. From this surface we will get another radiation. From this surface we will get another radiation, another radiation. So all radiation will march one point, and it will have some constructive interference. And at the point of constructive interference, we'll get the steered beam. So we can vary this eta and we can get the steered beam for this IRS. An operating principle, a lot of authors have discussed operating principle like love field equation, and some author have discussed that equivalent electric and magnetic current, and end-to-end model of IRS, parameterized wireless channel with adjacent fading channel. And some user also, some authors also discuss other like coupling our IRS model. This IRS can be fabricated with different type of techniques. So this is the first IRS. So here the authors they took the magnetodielectric spherical particle. So this spherical particle has tuning capability. So from each, I mean, for each particle, they have on different phase. So this is phase one, this is another phase, another phase. So it has some steering capability. This one is the another paper, and here there's a reflector. So reflector is same as the IRS, and here the author have used PN diode, and this one is another paper. In this paper, the author used the FPGA and sequence and coding sequence, and this is the programmable metasurface. So like trigger 0 1 2 3 4 different trigger, and this is the FPGA, and these are the controlling signals. So if for one controlling sequence, the programming metasurface will have one phase. For this controlling sequence, the programming metasurface will have different phase. So it will have some different um, different beam steering capability, and for this coding sequence, it will have different steering capability, like this type of thing. And this IRS can be fabricated with different type of technique, like a varactor diode. Varactor diode are commonly used to fabricate IRS. So this one is the one paper. This is fabricated cell, and the author have used here varactor diode to fabricate the IRS. And this one is the another IRS. Here also author have used varactor diode to fabricate this IRS. And this one is from UK. Here author also used IRS to fabricate. I mean, author also used vector diode to fabricate this IRS. And this is the phase, and this is the phase. So the phase is 0 to 360 degree, and this is the magnitude. So magnitude for different biasing voltage of the vector diode, the magnitude are different, and we can get a phase shift. Now this one is the another unit cell of the IRS. So here the author have used two vector diode for tuning this unit cell, and this is the total fabricated structure for this IRS. And IRS also can be fabricated, I mean RIS also can be fabricated with PN diode. So instead of vector diode, we can also use PN diodes. The one important thing of this PN diode is that the PN diode will have less complex structure. For this vector diode, we need a lot of phase shift, like this type of phase shift, like a lot of phase shifts. So the external circuit will be very complex. But if we use the PN diode, the external circuit will be very, I mean, external circuit will not be complex, but it will be very simple. So PN diode is very important for this RS design. And this is another 2-bit RIS design. So here the author have used total 5 PN diode to get 2-bit operation. And after that, and this figure is the magnitude for this structure, and this is the phase, and this one is the fabricated IRS. This one is the another IRS, unit cell of the IRS. Here the author used PN diode, and this one is the rectangular waveguide and PEC wall, and this one is the another IRS design. And here the author have used here PN diode, and it's a metal plate, and this is the biasing line. After that, the author fabricated the total RIS, and they checked whether it is working or not in actual scenario. And this one is the another IRS, 2-bit IRS. So the author have integrated 2 PN diode here, one PN diode, another PN diode, and they got uh, IRS. This one is the another IRS. So here this is one patch. After that, the author integrated here PN diode. and these are some biasing line. After that, author fabricated this iris, and this is the back side of the iris, and these are the reflection phase, and this one is the magnitude response for this iris, and this one is another fabricated ridge. After that, the author, they fabricated this different ridge, and they have used this type of power supply host computer to fabricate this, and this actually was fabricated by Samsung company. Here they have used two PN diode, one PN diode and another PN diode, and this is the DC ground plane, and this one is the RF ground plane. This is the top layer, and top layer we have some patches, and ground plane also patches, and these are the some biasing DC biasing line, and this is the 2-bit IRS. Now these are the reflective iris. The iris will have some reflective capability. Also, the rays can have a transmittive type. So the transmittive type is expected to pivotal in beyond 5G 6G communication, and this one is on fabricated the transmittive type is. Also, people are saying that these are the transmit array arrays, and author they fabricated the arrays of the transmit array. Now, energy harvesting wireless power transfer. So this one is the one was fabricated for wireless power transfer. So this one is the here one IRS, and there's a lot of block diagram here. After that, with this it is possible to get wireless power transfer, and this type of reads are known as eye surface. Also, the reads can be three-dimensional reads. One dimensional we have less we have less functionality, but for 3D type of rays we will have more functionality. Like here the author have used silicon oxide graphene to get the three-dimensional rays, and this one is the another iris. This one is the another iris, the fabricated iris, and most of the iris are only 1 bit or 2 bit, but iris can be 2.7 bit, 3 bit, or multi-bit. Like here, there are more than 1, 2, 3, 4 PN diode here, and the author got maybe 2.75 bit configuration. And this one is after that they fabricated 6x6 iris. This is another iris. This is the fabricated iris, and so the iris can reflect the signal, iris can transmit the signal. Also, nowadays different type of iris is being proposed. This type of iris is known as star rays, simultaneously transmitting or simultaneously reflecting rays. And iris will not only useful for transmitting or reflecting signal, but it should have some additional capability, additional function, like sensing the signal from which direction the signal is coming. So there are a lot of, in literature there are a lot of paper out there, and a lot of people are proposing different type of iris. So this one is the first iris where the upper surface. So this is the upper surface, and the upper surface the author are using some diode, and with this configuration they are getting the reflected steering capability. And after that the author introduced one via here, and from the via they are getting some signal, and from this signal it can sense the incoming signal, direction of arrival of the signal, from which direction the signal is arriving here. And this one is the another proposed iris in the literature. In the literature, the author have used the varactor diode here, and they have a lot of port, one port, two port, three port, four port, and from this all port it is possible to sense the signal. And for this type of rays, it is multifunctional rays. So for this type of rays, so from upper surface the beam will steer, I mean we will get beam steering capability. And from here we have here one via, here another via, from here via, and this one is the SLW structure. This one is the port 1, port 2, port 3, and port 4. So from port 1, port 2, port 3, port 4 we will get the sense signal, maybe some fraction of the incoming signal, so we can sense from which direction the signal is coming. Next, this one in another IRS. So for this IRS the same thing, that and the author they have used PN diode here, and after that just incoming signal is there, so incoming signal is coming here and it is impinging on the surface, and here some diodes are there. Because of diode we can change the biasing of this diode, so we'll get some steering capability from here. And here we have also some sense, I mean we have also some sensing port. From sensing port we can get the sensing signal, so we'll get both beam steering as well as sensing operation with this configuration. Now this is the fabricated IRS. Now this is another type of IRS proposed in the literature, and this is the side view, and this is the top view of the IRS, and this is the back view of the IRS. And this type of IRS is very important. Now the problem with this IRS is that the reflected signal, the power of the reflected signal is very small one. So to get very large amount of power from the reflecting IRS, a lot of people are using amplifying a structure. So amplifying structure, structure is that the authors are integrating some amplifier in the IRS structure. So this type of IRS is very important for future communication. And IRS can not only be fabricated with only PN diode or vector diode, also it can be fabricated with different type of other mechanism like liquid crystal, graphene, or vanadium dioxide. In here, the author used some vanadium dioxide to get the beam steering operation, and this one is the unit cell here, and this is the vanadium dioxide. And another thing is that recombinant intelligent surface which risk scattering. So this risk scattering will be very important for 6G communication. Here the author they have introduced this type of IRS for risk scattering. And the on-chip integration of the IRS is very important, because with only one chip we can integrate everything. So this one is the on-chip integration of the IRS. Now the author have some silicon dioxide to fabricate the IRS. Now passive type of IRS also very important. So this is our fabrication. I have fabricated this thing. So this type of risk is also very important. Liquid crystal. So we can also use liquid crystal to fabricated IRS. So this one is the fabricated IRS with liquid crystal. Now switching, how we can switch the IRS. So there are different type of switching mechanism like PN diode, vector diode, or we can use MEMS switching, or vanadium dioxide, or graphene, silicon, germanium arsenide, indium tin oxide, aluminum doped zinc oxide, different type of things. A channel is that, so the industrial body, they are looking for simple and cost effective risk. So the risk should be very cost effective for actual deployment. But the problem is that if you want to fabricate this risk is very expensive. So that's why a little bit difficult in nowadays to, I mean, to get this type of risk. Now I have discussed this thing. And this one is the 1 2-bit IRS proposed in literature. Here the author, they have used total 5 PN diode, one PN diode here, another PN diode here, another PN diode here, another PN diode here. With this 5 PN diode, the author is getting 2-bit operation, and this is configuration 1, configuration 2, configuration 3, and configuration 4 for different configuration. And the magnitude response is almost 1.1 dB or minus 1.2 dB or 0.8 dB or 0.8 dB, so for different configuration. And this one is the fabricated IRS. Now after that, what the author did, author used the USRP, Universal Software Radio Peripheral, to verify that this IRS is working in real-time environment or not. So this is the phase distribution of the IRS for broadside beam. And here the author, they use the transmitting host and one sub computer. After that, this is one is the USRP, Universal Software Radio Peripheral, and this one is the IRS, and this is the receiver USRP, and this one is the receiving host. So after that, this is the baseband signal. So for processing the baseband signal, FPGA processor and embedded processor used. So the embedded processor handle the media access control, that is MAC layer protocol, such as data framing, and this field programmable gate array, that is FPGA module, handle the physical layer signal processing, such as channel coding, orthogonal frequency division, multiplexing, modulation. And after that, this is the signal flow diagram. So this is the RF, this is antenna, DSC, and PS, SCP, IFFT, and HSP, and pilot and virtual carrier. This is a mapping and interleaving, and this encoder and data source. So this one is the transmitting section, and this one is the receiving section. For receiving section, here's the antenna. This is an analog digital converter, and we need to remove the CP here, SP. And this one is the FFT, a channel characterization here, channel equalization, and PS, and D mapping, D interleaver, and decoder, and receive data. So this is the total communication system for this 2-bit of IRS. And after that, the author, they checked different environments, so like different distance. So this is for one distance, the author checked what is the radiation pattern for this configuration, and the constructor was fabricated at 2.3 gigahertz, also 28.5 gigahertz. For 2.3 gigahertz, this is the radiation pattern, and this is the scan beam for 2.3 gigahertz. And this is another RIST proposed in the literature, and this one is the reflection coefficient, and this one is the reflection coefficient of the, this is amplitude and this is phase. And here the same type of configuration used. So first is that here, like previous configuration, here first is the FPGA board and control board. This is power supply, and this is the recombinant surface, and this is the host computer, and USRP, the antenna, here the host computer, and this one is the USRP, and this one is the host computer. So this is the total diagram for this IRS. Now author, they checked the performance of the IRS for different scenario. This for this scenario, the distance between the transmitter antenna and the IRS is 50 meter. For 50 meter, this is the transmitter, and this one is the IRS, and maybe this one is the receiver, and this is the radiation pattern for this configuration. After that, the author put the IRS in 50-meter distance. When there is no IRS, the received signal power was minus 67 dBm. But when there is IRS, the received signal is minus 53 dBm. So there is a significant amount increase of received signal because of this IRS. This one is another fabricated IRS. So here one vector diode, and this is the same thing, and this is the equivalent circuit of this IRS. And this one is the phase. The author used microcontroller, a digital to analog converter, operation amplifier, and this group is are from UK. So here the IRS, this is the horn antenna, and this is the VNA, and this is the phase of this IRS, and this is the experimental setup for this IRS, and the experimental campaign test setup in room 1 and test setup for room 2, and this is the receive signal at the ASDR developed in two cases. This is switch off IRS when there is no IRS and configure IRS scenario. So this one type of IRS I've discussed. So IRS can be different type of, like we can classify IRS into different group. If the diagonal matrix with respect to diagonal matrix of the IRS, diagonal matrix with the IRS can be classified reflective type or transmittive type. So this is the classification. This is beyond diagonal IRS. So beyond diagonal IRS can be classified different type of things like hybrid mode, multi-sector mode, or deflecting mode and deflecting mode. So again, this is the another IRS star is simultaneously transmitting a is, and this is multi-sector is and dynamic grouping and different type of is. So we can classify this as the beyond diagonal matrix is. This is this classification tree. Now this is the two-dimensional is, that is, this is the diagonal matrix are all zero, but if the diagonal matrix are not zero, then we can get the beyond diagonal matrix is. So this type of is are also known as reconfiguration surface 2. Here you can see from this rays, it has only reflecting capability, only the beam will be reflected from here. But for this type of rays, it has both reflective type capability as well as transmittive type capability. And for this type of rays, uh, we are getting different radiation pattern. This is one radiation pattern, this one is the two radiation pattern, 3, 4, 5, 6, 7, 8. So 6 radiation pattern for this type of for from this rays. So these rays are known as reconfiguration surface 2 rays. And so this is the some user case, the reflective use. So let's say we have some user there. So user 1 here and user K1. So this type of rays can reflect some signal from here to this area, and it can reflect transmit some signal from here to this area. So this type of rays are known as the beyond diagonal reconfiguration surface rays. So it has both transmitting and reflecting capability. Now this is another type of IRS, and this is not cell wise single connected multi-sector beyond diagonal rays. So we have one transmitter here, and the user 1, user 2, user 3, etc. until user K1. So we can have different user here. Also we can have different user here, different user here. So different user here. So the beauty of this type of this is that, so we have one signal. Uh, we have one signal. So from here we are from here we are the signal is coming and going here, and after that the signal can go here this way and this way or this way. So this type of rays are known as cell wire signal connected multi-sector beyond diagonal rays. And this is the reconfiguration surface 2. Like we can use this type of iris here. So let's say we have this type of iris here. Now we have the tower here. So this one is the transmitting tower. So from the transmitting tower we can get some signal, and from here we can get different signal from different area, from here, from here, from here, from different area. Also we can connect a different aerial, like integrated sensing and communication, or black hole access, or wireless sensing devices, or different, we can connect different areas. So this is the potential, these are the potential application of the beyond diagonal arrays. Also, this type of bridge can be used for wireless power transfer. So we, let's say this is the main tower, and this small pico tower for beyond 6G communication. So from this pico tower, the the signal can go from here to this beyond diagonal rays, and from here we can get some wireless or sensor wireless power transfer from different area for different sensor node. So this type of rays will be very important for future communication. Now, this type of rays are known as a star rays, that is simultaneously transmitting and simultaneously receiving rays. So here we have some tower is there, 6G tower. From 6G tower, the T and T mode are incident on this iris, and some, let's say some T mode is reflecting here, and some T are reflecting going there. So we'll get this type of rays. This rays are star rays. And after that, the author they fabricated this rees, and they checked what is the S1 parameter and S2 parameter for this type of rees. And this is the S1 parameter of this rees, and this is the S1 parameter for this measure rees. And after that, they have compared this iris for different with with different proposed in the literature. And for this configuration, let's say we have this type of phase distribution. For this type of phase distribution, we are getting the beam will stay here. For this phase distribution, the beam will go here. For this distribution, the beam will go there, different locations. So for different phase distribution, we'll get the steer beam patterns. Now this one is the normal another iris. So for this iris, let's say this is for normal. We have one iris here. For if this is for normal incident, so the wave is coming from here and it reflecting. Wave is coming from here, and after that the wave is reflecting. But for this proposed rays, the normal incidence like there, and this is the anomalous reflection, and this is the anomalous transmission. So for this type of rays, we are getting anomalous reflection as well as anomalous transmission. And this one is the proposed rays for this configuration. This is the top layer iris, and the iris was working at 0.85 terahertz frequency band, and another working at 0.4 terahertz frequency band. And this is the E field, and this is the EX, and this is the EY, and this is the EY for a transmission at frequency 1. This is one frequency, this is another frequency. After that, the author they put different configuration and check the different type of field configuration for this type of reconfiguration surface 2. So integrated sensing areas is another important area of communication. So we don't need only the steering capability, also we need sensing capability. So this is one very important design here. In this design, there is a lot of unit cell are here. So this is one unit cell, two unit cell, lot of unit cell are here. Now here the author have included one via. From here they are getting some sense signal, and after sensing, this is the rod mesh lens, this is the power detector and power pin and output pin, and from here we can get the sense signal. So we can estimate from which direction the signal is coming. So we can get both steered beam as well as sense from which direction the signal is coming. So the integrated sensing and communication is also very important for 6G communication. And this is a structure, how we can get integrated sensing and communication. Now a lot of people are proposing this type of antenna, that is this type of antenna, that is smart electromagnetic environment. And here we can use this type of antenna here. Suppose this is the transmitting horn antenna from a radio tower. From here the signal can reflect from here, after that it can come here, and again it can reflect the signal from here, and like this in this scenario. So this type of scenario is very suitable for 6G application. Also this one is another antenna. Here the radiation pattern are like this type of, so it can cover all directions. So nowadays a lot of people are also proposing this type of smart antenna too. So like this one is the phased array antenna. After that the have author have used this type of curved surface, and this from curved surface we can get the steered beam. Now transmit array. So transmit array is also one type of bridge. So what is the advantage of a transmit array? Like this one is the phased array antenna. For phased array antenna, we need here one phase shifter. The problem with the phase shifter is that minimum loss may be minus 2 dB or minus 3 dB to minus 7 dB. So there will be significant loss for the normal phased array antenna. But instead of normal phased array antenna, if we use this type of transmitter antenna, then the loss will can be minimized. So the limitation of this type of phased array antenna is that large insertion loss. Number two is the very expensive. Number three is the largely high complexity in configuration, bias fit network, low radiation efficiency. Advantage of these things: the low insertion loss, less expensive, and easy to fabricate. And a lot of people have proposed a lot of different type of transmit array. Now we have also proposed one transmit array here. Also we have proposed one transmit array. So in future, maybe a lot of people are going to propose different type of transmit array. That is the 2-bit transmit array, 3-bit transmit array, or 4-bit transmit array. And also this transmit array can be integrated on antenna substrate. So normally transmit array are like this one. The horn antenna is there, and this one the transmit array. Also this transmit array one type of IRS. So we can integrate this transmit array into this antenna also, and also dielectric unitary antenna can be integrated to this transmit array. Use of metamaterial on the substrate and near field coupling, use of 3D printing material. So this will be the future of transmit array. Now this one is our proposed design. So in this design, and this one is the top patch, and this one is the bottom patch, and we have here one conductor, and this one is the biasing line, and two vias are there. But the thing is that it's very expensive to fabricate. It took almost 8 lakh Indian rupee to fabricate this only one structure. Extremely expensive to fabricate. We have used Teconic RF35, that 1.6 millimeter, and this one is the 3D view of the unit cell. And after that, we put our unit cell into this configuration, that is waveguide. And after that, we have checked and the simulated and measured transmission coefficient for state 1, and this one is the simulated and measured magnitude of the transmission coefficient for state 2, and this is measurement setup with VNA and power supply. And here we proposed one polarization, I mean, we have proposed here polarization conversion IRS. That is, with this IRS we can get converted polarization. So here we have one PN diode, there is another PN diode, this is via, this is top view and bottom view, and this one is the fabricated top view and bottom view of our unit cell. And this transmitter unit cell designed for beam steering. So with this unit cell we can get only steer beam, and these are the S11 parameter, S21 parameter, S22 parameter with 2 into 2 unit cell for cooperation state with the waveguide. And this one is the magnitude of S11, S21, S22 with 2 into 2 unit cell for polarization converted with the waveguide. And this is radiation pattern E plane and H plane radiation pattern with no polarization conversion, and this one is the E plane and radiation pattern with polarization converted state. And after that, we design transmit array that has both beam steering as well as polarization conversion capabilities. So with this configuration, it is possible to get both steered beam as well as polarization converted beam. Now this one is the upper patch. In upper patch we have 2 PN diode, and lower patch we have 2 PN diode. With this 2 PN diode we can steer the beam in one direction, and with this 2 PN diode we can change the polarization. From this 2 PN diode we can change the polarization, and with this PN diode we can get the steered beam. So with this configuration, we can get both a beam steering as well as polarization conversion properties. So we have a different state, that is state 1, state 2, state 3, state 4 for this configuration. Now the power, how much power we need for this type of configuration. So we have calculated for this type of configuration we need almost 40 milliwatt power. Actually our design was 20 into 20, so almost 40 milliwatt power for a total design. Now this one is our favorite, this one is our 8 into 8 transmitter with biasing line. So this is one transmitter, and this one is the biasing line. This is another transmitter, we have another biasing line. So these are the unit cell, and this biasing line are for polarization conversion, and this biasing line is for the beam steering capability. So we are getting both beam steering capability as well as polarization conversion. And this is radiation pattern for 8 into 8 array for state 1, and this one is the radiation pattern for state 3. Now this one is our proposed design. Let's say we have phase configuration, phase distribution for this type of transmitter. For this phase distribution, the radiation pattern is like this. For this phase distribution, the radiation pattern is like this one. For this phase distribution, the radiation pattern is like this one. So with different phase distribution, we are getting the steered beam, and we have calculated how can we get the steered beam. And this type of transmitter, the radiation efficiency, radiation and aperture efficiency is very important, because for practical application, aperture efficiency should be at least 60%, something like that. But in literature, a lot of people are proposing aperture efficiency maybe 20% or 25%. And this one, our 4 into this one, or 4 into 4 transmit array, and this is the transmitting aperture, and this one is the receiving aperture. So simulated measure transmission and reflection coefficient for state 1, a simulated and measured phase for state 1 or state 2, and this one is the simulated and measured phase of the transmission coefficient for state 3 and state 4. Now this is our fabricated transmit array. This one is our fabricated transmit array. So this one is the E-plane simulated and measured radiation pattern, and this one is the E-plane simulated and radiation pattern for state 1. This is the for state 2, state 3, and this one is the state 3 radiation pattern. Now integrated sensing and communication is another important area of research. So in this design, we have designed one unit cell which has both beam steering as well as sensing capabilities. So in the upper patch, so this one is the upper patch. In upper patch we have 4 parasitic patch, 1 patch, 2 patch, 3 patch, 4 patch, and we have 2 PN diode, 1 PN diode, another PN diode. And here we have one via. From via we can get some impinging signal, and this one is the SRW structure. So some signal will be collected from here, and we can sense the signal. Like previously I discussed that one sensing, integrated sensing and communication. So this is also from Korea. Here we can use this type of sensing port. After that, Rotman lens and power detector and power pin, and this one is the output pin. So this one is our proposed design. This one is our proposed design. Here also we can use this type of rod mount lens and power detector from here, and we can get the beam steering as well as sensing capability, because now that interior sensing and communication is very important for 6G communication. So here the unit cell has total 5 layer, and isola itera empty substrate with permittivity 3.45, loss tangent and 0.0031 was used in our configuration, and this configuration is 2-bit design. And here we have used the Floke port to design this configuration, and we have DC ground plane. Also have we have millimeter ground plane, because this 2-bit IRS with sensor working at 29 gigahertz frequency band. SRW structure was integrated at the bottom of the unit cell to collect a small portion of the incoming signal for sensing purpose. And our design is almost 2-bit with sensing capability. So this structure is the input version of the all the study published in the literature. Now these are the current distribution. This is magnitude of electric field for state 1, and magnitude electric field for state 2, magnitude electric field for state 3, and this is the state 4. Now this configuration I have used SRW technology. So SRW technology, last yesterday I was discussed what is SRW technology. So the SRW technology is same like waveguide technology. It will only support TE mode, but it cannot support the TM mode, because for TM mode the slot and the current are in perpendicular 90-degree direction, so it cannot support the TM mode, only TE mode. And this SRW structure preserves all the advantage of conventional waveguide, that is high quality factor, high power handling capability, will self-consistent electrical shielding. Now this 2-bit was designed at 29 gigahertz frequency. So we have one state, another state, another state, and the total 4 states are there. At 29 gigahertz, the magnitude of the replacement coefficient was minus 1 dB, minus 124 dB, 0.4 dB, and 0.35 dB. The value of the phase of the reflection coefficient at 29 degree for different state of the unit cell were 25 degree and minus 21 degree, 80 degree, and minus 102 degree respectively. Now this is the magnitude of electric field at the sensing port, and this one is the simulated magnitude of the electric field at the bottom of the unit cell, the amount of sensing in the waveguide. So from this figure we can figure out that how much power is being sensed with this configuration. At 29 gigahertz, the amount of sensing was minus 20.7 dB. One port was at the waveguide port, another port was placed at the sensing area. Now after that, we put our design into waveguide. This one is the waveguide structure here, and we design 1 into 3 unit cell. This one is the front view, and this is the port configuration for measuring sensing, amount of sensing. 1 into 3 unit cell with waveguide with via front 3D view, and this one is the waveguide structure, and this is the S1 parameter. We chose WR28 waveguide, which can operate from 22 gigahertz to 33 gigahertz, and this each unit cell size was 5 millimeter into 5 millimeter. However, the size of the aperture of the was 7.112 millimeter and into 3.556 millimeter, And this magnitude of reflection coefficient for different state, and this one is the phase of reflection coefficient for different state. At 29 gigahertz, the value of magnitude of reflection coefficient with different with waveguide model was minus 1.05 dB, minus 1.3 dB, 0.85 dB, and minus 2.7 dB for state 1, state 2, state 3, and state 4. At 29 gigahertz, four distinct phases were observed. Now this one is the another design. Here we this one is the passive reflector, passive IRS. So this one is FR4 substrate. This is the ground, and there's air gap between FR4 substrate and ground. And here we have some one configuration, and these are different configuration. For this configuration, we are getting steered beam. The steered beam are the fixed steered beam, like for only one circular production 30-degree incident, and when there's a PEC the 30-degree incident, this type of reason, and when only ring type of patch 30-degree incident, and ring and patch combined, that is a 0-degree incident. After that, we measure our structure in this type of environment. So this is the VNA, and this is our proposed structure, and we measure S21 parameter for circular patch, and this one is the S21 for ring patch, and magnitude of the S21 parameter for different configuration. The only when there's only one patch or PEC or mixed or without IRS or with ring, and measure and simulated was reasonable with 3 to 4 gigahertz frequency range. And this one is another design. In this design, we have used on vector diode here, so we can tune the vector diode to get the steered beam. And this one is the S1 parameter. This is the phase of the reflection coefficient for different values of the capacitor. And energy harvesting for RES. So maybe some fabricated prototype are there for energy harvesting of RES, but in literature, very few paper are there. Extremely, I mean, very less number of paper are there for energy harvesting for RES. But theoretical people, I mean, the communication people, they are publishing a lot of paper that suppose we have this type of IRS structure, and here we can integrate it RF, some absorbing unit cell. These are the absorbing unit cell, and these are the reflecting unit cell. So the reflecting unit cell can be used as a normal reflective type of IRS. So from here we can get the steered beam, and for this absorbing unit cell we can get the energy harvesting for IRS. Also, a lot of paper, theoretical paper are there. So this is the wireless communication paper. These people are publishing a lot of paper that we can design this type of thing. But in fabricated, there's a very few number of fabricated prototype in the literature. So conclusion, we have discussed basic of 6G and recombinant surface. We have discussed previous of recombinant surface, and I have discussed our work transmit and rest, also energy harvesting operation. Thank you. These are references, and thank you.
Hello, am I audible?
Yes.
Yeah, so thank you, Dr. Rana, for your valuable and rich presentation. So now I will ask participants can raise any type of questions if you have.
Sir, I have one question, sir.
Yeah, please go ahead.
Hello,
Yeah,
sir. In your sir, in our presentation, we provide the S11 and S21 parameters. The
Yes.
S11 mean return loss. Return loss. This value is always minus 10 dB below mean is good. But S21 denote which parameter, sir? Then there is an limited. For S21 parameter limit values, sir.
Oh, this
Hello.
is very available in book. You can read any book. So from book you can get what should be the S1 parameter, what should be the S1 parameter.
S21 actually, in my opinion, the question is asked by Bhavani Shankar. Am I right?
Yes, sir.
Hello, am I audible?
Yes, sir. Yes, sir.
Yeah. Actually, Bhavani, the thing is that, in my opinion, there is no limiting parameter for S21. S21
Yes, sir.
refers to
Okay, sir.
the S21 refers to the mutual coupling between two individual elements. Okay. So there is no
Yes,
limiting
sir.
parameter. Only by the definition of IEEE, the standard S1 should be below minus 10 dB for the general impedance matching characteristics.
Yes, sir. Thank you, sir.
So any other questions? Okay, so Dr. Rana, I think that there is no other questions over there. So thank you once again for your valuable presentation. So now I am ending our session over here. Again, we will come back at 7:30 with the same link.